All right, hello, and this is video number 2 of section 3.2. So we're just going to pick right up where we left off last video. Well, sort of. What we're going to do now is we now have the tools to prove the theorem behind me, which I've been hinting at a little bit, I think, in some of the lectures, but we can now state definitively. And then we're going to prove 2 more very cool properties about determinants and do some what I think are really fun problems, because they let us sort of use these theorems in sort of creative ways, and they're just fun puzzles to work through. So this theorem, which is, again, we've been discussing this a little bit, but an n by n matrix is invertible if and only if its determinant is non-zero. So you might be asking, haven't we already shown this? And the answer is sort of. Because we've shown one direction of this if and only if statement. So remember that an if and only if statement means that both things have to imply each other. That means I should be able to show that if A is invertible, then its determinant is non-zero. But I should also be able to show if its determinant is non-zero, then A is invertible. So we've seen this direction. Because this was sort of the motivation for having introduced determinants, right? Remember, we introduced the determinant by discussing it as this sort of relation or expression you get as a result of row reducing sort of a general n by n matrix, right? And so we remember then sort of pointed out that the determinant then, or that this matrix was invertible, right, if and only if that sort of corner entry, which ended up helping define the determinant, was non-zero, along with all of the other entries with it. There's a lot that went into it, but one of the big sort of key points from that was that we had this thing which we knew if A was going to be invertible had to be non-zero. And so we've already discussed this and shown this. What we haven't shown is the other direction. And so that's what I want to show now, is that if the determinant of A is non-zero, then just this knowledge alone is enough to know that A is invertible. And what's amazing, remember, is that all of those other things in the invertible matrix theorem follow along from this as well. So you can actually add this as an extra sort of statement in the invertible matrix theorem. All right, so why is this true? Well, so remember from what we did in the first lecture that we can row reduce A using k row swaps. And here, remember, k can be is just any number, integer, 0, 1, 2, 3, 4, 5, just counting the number of row swaps, but it can be 0. Using k row swaps to an upper triangular matrix, B. All right, so why does this help us? Well, we know that in doing so, right, then the determinant of A is equal to -1 to the k times the determinant of B. Okay, so why does that help us? Well, this here helps us because if the determinant of B, which remember is the product of its diagonal entries, is non-zero, then we know B can row reduce the identity matrix. And real quick, I'll give you an example of why. So let's just say I had this arbitrary matrix and circled its diagonal, right? So this matrix is upper triangular. So the diagonal entries are 1, 2, and 3. So we know that the determinant of this matrix is equal to 1 times 2 times 3, which is 6. But even more than that, I can look at this matrix and I can tell you that this matrix will row reduce to the identity. Because, notice, this 3 will clear out the column above it. This 2 will clear out the column above it. And then it's just a few more steps to get the identity. So if there are n, or in this case 3, but we're saying n in general, if all of the diagonal entries of B, so all n of them, are non-zero, then B will row reduce to the identity. Not that we need the second fact here, but notice, alternatively, if one of the diagonal entries of B were to be non-zero, notice, well, first off, the determinant of this matrix is 0. Or sorry, if one of the diagonal entries of B was 0, the determinant of this matrix is 0, and because I have this row of all zeros, this matrix will actually not row reduce to the identity. So the importance of this and this is that, well, by assumption, so by this assumption, since the determinant of A is non-zero, well, because of this means the determinant of B has to be non-zero, right? Multiplying by -1 any number of times is never going to make something equal 0 that wasn't previously 0. Since the determinant of B is non-zero, as we saw, so this means that B and A row reduce to the identity matrix. So notice that we showed that B reduces to the identity matrix, but this also implies that A reduces to the identity matrix, because remember, we got to B by row reducing A, right? So we're just tagging on those extra row reduction steps to get all the way from A to the identity. And then the invertible matrix theorem takes care of the rest. So an n by n matrix A is invertible if and only if its determinant is not equal to 0. All right, so I'm going to state the next theorem. I will probably include an example of this in the worksheet, so you can work through and get a slightly better picture of why this theorem is true. So I highly encourage you to work through that. Depending on what I need to put in the third video for this section, I may or may not also include it. Well, certainly there'll be a solution in the worksheet, but I might talk about it more later on. But this theorem just states that if A is an n by n matrix, then the determinant of A is equal to the determinant of A transpose. So like I said, I think the reason why for this is very easily seen just doing it with a matrix and its transpose, and so I'll include one of those on the worksheet. But just for time's sake with the video, I don't want to go through the process of calculating two determinants to see it, so I'll at least definitely include that in the solution. But to see this, notice that column I of A is equal to row I of A transpose, right? And this is true for every column and row. And then on top of that, right, row I of A is equal to column I of A transpose. So all you do is use cofactor expansion to sort of verify this is true. Use cofactor expansion. Across row 1 of A and column 1 of A transpose. And so notice in particular, row 1 of A and column 1 of A transpose are equal. And the way the rest of the numbers get shifted around when I take the transpose, in fact, every single step of this process is going to be the same doing the cofactor expansion. And remember, using cofactor expansion will get us the determinant, sometimes in a less than, in a more roundabout way than we know how to do so now, but it's still useful for proving things like this. So I don't want to go too much more into detail on this for now because, well, just because it would take more time than I think the video has, given what I want to get through. But just remember this, that the determinant of A and its transpose are always equal, much like other properties, right, that A shares with its transpose. All right, so this is sort of it's also sort of theorem 5 is going to be the least used theorem, I think, that we talk about. It's important to note, but I also really want to get to theorem 6. But before I do that, I do want to look at an example. So we're going to let A be the following matrix: 2, 3, 1, 4. We're going to let B be the matrix -2, 4, 5, -1. And we want to calculate the following 4 things. We want to know the determinant of A. We want to know the determinant of B. We want to know what is the matrix A times B. And then given that matrix, we want to know what is the determinant of the matrix AB. So I recommend actually pausing the video here and going through it on your own. After calculating all 4 of these, see if you see any interesting patterns. All right, so doing this, I got the determinant of A was equal to 2 times 4, which is 8, minus 1 times 3. So 8 minus 3 is 5. The determinant of B is equal to -2 times -1, which is 2, minus 5 times 4. So I got -18 for the determinant of B. Doing the matrix multiplication dance to calculate the product of these 2 matrices, I got 11, 5, 18, 0. All right, well, we can now use this matrix to calculate the determinant of A times B. And maybe you see what's happening here, because the determinant of A times B is equal to 11 times 0 minus 5 times 18, which is equal to -5 times 18, which is equal to -190, but that number isn't as important. Look at these 2 numbers and look at these 2 numbers. So in this example, we just showed that the determinant of A times B was equal to the determinant of A times the determinant of B. That is, that the determinant obeys the multiplicative property in this example. Well, we all know that one example doesn't necessarily equal a trend or a theorem, but in this case, it does. And so this is a really cool theorem. I think one of the coolest things we've seen so far, just because it's so surprising in a way. But if A and B are n by n matrices, then the determinant of their product is equal to the product of the determinants. And this is true for every pair of n by n matrices A and B. And so the proof of this will definitely be provided in the next lecture because I think it's interesting and provides some insight as to what's going on here. But this is, again, extremely, just so cool that we get something like this. And we will use this fact very often. And so I actually do want to number this theorem. So this is theorem 6. So I'll put a box around this just because it's so important. So if A and B are n by n matrices, then the product of the determinants, or the determinant of the product, is equal to the product of the determinants. All right, so I want to end with some examples, but before I do that, I want to give you a very important warning about this. So this is called the multiplicative property of determinants. It is tempting to want to also apply, because we've seen a lot of things where this does work, an additive property. That is, it's tempting to say, but it is not always true, that the determinant of A plus B is equal to the determinant of A plus the determinant of B. So another way of thinking about this, and I'll put a big red circle around this. See, this means that it's very scary. So it's not always true that the determinant of A plus B is equal to the determinant of A plus the determinant of B. I think it's just tempting because we see a lot of operations where this can happen, but just know in this case, this is not always possible. And so just be very careful about this. Like always keep this sort of in your mind while you're working. So multiplication, you can split up determinants all you want, and we'll see some examples of that here. Addition, no can do. All right, so with that out of the way, let's do some fun stuff. So I've left a handful of example problems on the worksheet, and you'll get one or two of them on your homework. Really make sure you know how to do problems like this, because it's almost guaranteed that I put at least one or two of these on the test, or on the midterm, which is coming up very soon. I think at the time of the schedule, when this video is scheduled, the midterm is 2 days from now. So these examples we want to answer, and what we want to do is either calculate a determinant or explain why something's true. But we actually don't want to do much calculation. We mostly want to use the theorems and theory and sort of facts that we've learned about determinants to do these things. So, first problem. If A is an n by n matrix, and the determinant of A is equal to -3, what is the determinant of A inverse? So pause the video. You have enough information to do this using the theorems that we've learned. We know that the determinant of A is -3. What is the determinant of A inverse? All right, so how do we determine the determinant in this case? It'd be a fun TV show, Determine the Determinant. It has a nice ring to it. So notice that A times A inverse is equal to the identity matrix. Well, because of this, we know that the determinant of A times A inverse is equal to the determinant of the identity matrix. Well, the identity matrix is a diagonal, so technically upper triangular, matrix with only 1s on the diagonal. And so the determinant of the identity matrix is equal to 1. But we just learned that determinants can split up across multiplication. And that was very off-centered there. But we know the determinant of A is equal to -3. Well, if A, determinant of A times determinant of A inverse equals -1, this means that the determinant of A inverse is equal to -1/3. And so this is actually true in general if A has a non-zero determinant, that A is just its reciprocal. All right, so one more example, and I'll let you try the rest on your own before giving the solution, or the solutions. I'm not exactly sure how many are going to be on the worksheet when I finally release it, either 1 or 2 more. So suppose A is a square matrix. And the determinant of A cubed is equal to 0. And so the question is A invertible? So like I said, take a minute, think about it. All right, so the answer to this, no. So what is the reason? Well, taking this, because the determinant of A cubed is equal to 0, this means the determinant of A times A times A is equal to 0. And we didn't show it, but you can actually split up determinants across any number of products. And so this implies that the determinant of A times the determinant of A times the determinant of A is equal to 0. But notice, each of these 3 numbers are the same, and their product is equal to 0. So this means that, well, the information here is a little redundant. This implies that the determinant of A is equal to 0, and by theorem 4, A cannot be invertible. So, like I said, there'll be a couple more problems like this on your worksheet, and then 1 or 2 more on your homework. I highly recommend trying them. I think they're a lot of fun, and they're very, very nice problems.